Hello and welcome to our first question of linear programming, where we are trying to solve a greater than inequality. Our constraint is in type of greater than. So if you remember our previous lecture, we saw that whenever we come across greater than inequalities, we need to switch to either the big M method or two-phase method. So for now we will be talking of big M method. We'll talk of two-phase in lectures to come. So we'll put up a question over here and then we'll see how it is working. We're taking it as Z minimization. Z minimize is equal to 4x1 plus x2. 4x1 plus x2 subject to certain constraints. Those constraints are 3x1 plus 4x2. 3x1 plus 4x2 is greater than equal to 20. Then there is another constraint, minus x1 minus 5x2 minus x1 minus 5x2 is less than equal to minus 15. And of course, there is a physical constraint that x1 and x2 cannot be less than 0. They should be greater than 0. So this is the problem. For the first time ever, we are talking of Z min. Up till this point, we have taken questions where we were talking about maximization, Z max. Today we will be talking about Z min. Then there is an inequality which is of type greater than. So we need to go to big M. Obviously, when something is of type greater than, we need to go to big M method. Then there is an inequality in which RHS is negative. Let us talk about this inequality first. This inequality says minus x1 minus 5x2 less than equal to minus 15. Now, if we say that left hand side is less, then what we'll do? If we say that left hand side is less, then we'll add something. If this is less, I'll add something so that it becomes equal. Now when we try to find out IBFS, what we'll do is, we'll put decision variables and surplus equal to 0. This is our condition. Now we do not have a surplus variable over here, rather we have a slack variable. We have two decision variables. So what we do is, we put decision variables equal to 0. So this becomes minus 0 plus S1 is equal to minus 15, making it S1 is equal to minus 15. A negative IBFS is not permitted. We have seen in previous questions also that when we are starting a problem, your RHS or your IBFS cannot be negative. We cannot start with a negative solution. So this constraint is some kind of catch. This is also some kind of catch because for the first time we have a greater than kind of constraint. This is also a catch of sorts because up till this point we have done Z max questions, maximization, we were optimizing, maximizing our key variable. For the first time we are minimizing our key variable. For the first time we have an inequality or a constraint which is of type greater than. For the first time we have an inequality or constraint in which RHS is negative. So we'll see what we can do about all these things in steps. First step is, this is not permitted. So how do I convert it? We have talked about these, that we cannot start with a negative value, negative RHS. Remember, what we do is, we multiply the complete equation to minus 1. This complete equation will be multiplied to minus 1, making it minus x1 into minus 1 will become x1. This will become plus 5x2. This also gets multiplied by minus 1. The sign also gets multiplied by minus 1 and it converts to greater than. The less than becomes greater than. This minus 15 will become 15. So this becomes my constraint. So when I see this constraint, I should always know that it is not this kind of constraint, it is actually this kind of constraint. After proper modification, it will become this kind of constraint. So it is not a less than kind of constraint, it is not a constraint which will follow, which will move ahead with slack, rather it is a greater than kind of constraint and it will move ahead with surplus. And wherever we have a surplus variable, we have an artificial variable. So for now, this gets converted into this. So what I'll do is, I'll put a mark over here, or rather let's say converting RHS of second constraint into positive. So for second constraint, I am converting the RHS into positive. How? By multiplying it to -1. We've seen this. So this becomes x1 plus 5x2 greater than equal to 15. So this becomes my second constraint. So before even starting Simplex, I have converted my RHS which was negative. So this was an additional step to make sure that all RHSs are positive. Now we can start our problem from here. How do we start our problem? We need to convert these inequalities into equalities, and then whatever variables are introduced, like a surplus, artificial slack, whatever variables are introduced into our constraints, while we are converting the inequalities into equalities, we will add all those constraints into objective function also. The idea is whatever variables you are making use of, may it be a slack, surplus, artificial, to convert these inequalities into equalities, you will introduce all those variables in objective function also. Let us see how we do that. Let us convert these inequalities. First constraint is 3x1 plus 4x2. Now this is more than 20, it is greater than 20. So I need to deduct something. So I will be putting a surplus variable. And if you remember the previous lecture, we need not discuss it again. If you do not know why I am doing this step, you can refer to this, refer to the previous lecture. What I will be doing is, because I have a surplus variable, surplus is always accompanied with an artificial variable. If you remember from previous lecture, this will give me a negative start. Minus S1 will become equal to 20, S1 equal to minus 20. So in order to avoid that negative start, we are putting an artificial also. So whenever there is a surplus variable, there will be an artificial variable also. Again, if you are not sure why we are doing this, refer to the previous video. I will put up a link over here in the I that we have in this corner, or I will even put up a link in the description. So we have a 3x1 plus 4x2. Because it was greater, I have deducted something. Now because it is a surplus variable, I have added an artificial variable. This becomes equal to 20. This one is minus x1, sorry, we are not using this, rather we are using this one. We converted this. We converted this while we were removing the negative RHS. So we have this constraint. This is no more my constraint. This is my second constraint. What is it? x1 plus 5x2. Now again this is greater, so I need to deduct something. Surplus plus second artificial is equal to 15. So I have converted all my inequalities into equalities. Next, I need to include all these new variables that I have made use of, S1, S2, A1, A2 into my objective function. How do we go about that? Zmin is equal to 4x1 plus x2. These were the decision variables and key variables. This was the earlier relationship, but now I have 4 new variables. I need to incorporate these 4 variables also into my equation. So what about surplus? Surplus are easy, 0 S1 plus 0 S2. As we were doing in maximization cases, as we were doing in less than cases, as we were doing in slack, so is it in surplus also. But what about A1, A2? Remember, it is a minimization case. A1, A2, For A1, A2 we make use of big M, M A1, M A2, and for minimization it is plus M1, plus MA1 plus MA2. If it were a maximization case, it would have been minus MA1 minus MA2. So if it is a max, we make use of negative signs. If it is a min, we make use of positive M's. So this is about big M. So ours is a minimization case. So I'll be putting a plus MA1 plus MA2. So up till this point everything was same, but for this artificial variable we have a big M. Big M is a number which is very large, larger than any of the numbers visible in my linear problem. So this is it. Can we go for IBFS? What will be my IBFS? How do we find out IBFS? Putting all decision variables and surplus variables equal to 0. Put all decision variables and surplus variables is equal to 0. Decisions are 0, x1, x2 are 0, surplus is also 0. So my IBFS becomes A1 is equal to 20. From second it will become A2 is equal to 15. This is my IBFS. Now let us form our initial simplex table. Our initial simplex table would be we have a theta b, then x1, x2, s1, s2, a1, a2, all variables will be coming over here. a1, a2, s1, s2, x1, x2. And what are their respective contributions? We get them from objective function. So we have contributions of 4, 0, 9, 4, 1. We have contributions of 4, 1, 0, 0, m, m. 4, 1, 0, 0, m, m. These are the contributions. What is my IBFS at this point? A1 is equal to 20, A2 is equal to 15. A1 is equal to 20, A2 is equal to 15. Right? And what will be over here in table? The constraints. We have first constraint is 3, 4. A1 is coming from first constraint. A1 is equal to 20 is coming from first constraint. So we have first constraint over here 3, 4, minus 1, there is no S2, 1 and 0. From this constraint we get 1, 5, 0, minus 1, 0 and 1. What are the contributions of A1 and A2? M, M. We have Cj and then we have Zj. What is Zj? Zj is sum product of all columns with their respective contributions. First column with respective contribution, second column with respective contribution. Now, the first difference between our tables. Earlier we used to see that Zj was always 0 for first table because we used to have 0 over here for slacks. So everything would become a 0. But this time let us see what it is. It is 3m plus 1m. So I have a Zj of 4m. It is not 0 this time. Then we have 4m plus 5m, that is 9m minus m minus m, m and m. These are our ZJs. Another difference. Remember what we saw? For Z max, we take Cj minus Zj, while for Z min, we take Zj minus Cj. This is the only difference between Z max and Z min. There is no other difference. Yes, when you refer to a book, it might say that we will take Cj minus Zj, we will take most negative, we will take most positive, leave everything aside. It is exactly same as maximization case. The only difference being Zj minus Cj. Instead of taking Cj minus Zj, we should take Zj minus Cj. Books would convert this objective function. They will convert this minimization into maximization. They will write Z max is equal to minus 4x1 minus x2. Why convert so many things? Why not convert only one formula of net evaluation row? Earlier net evaluation row used to be Cj minus Zj. Now I will take my net evaluation row as Zj minus Cj. This is the only difference between max and min. The differences between greater than and less than are visible over here. Surplus and artificial. This is the difference between greater than and less than. But difference between max and min is Cj minus Zj or Zj minus Cj. So we have Zj minus Cj. Instead of going Cj minus Zj, I am going Zj minus Cj. What will be my first Zj minus Cj? It will be 4m minus 4. Next would be 9m minus 1. Next would be minus m, m minus m would be a 0, 0. Now because this is our first question ever about greater than, about minimization, let us talk about everything. These two are 0. No issues. They will neither improve my solution nor they will be making my solution worse. They are neither doing any good nor doing any bad to my solution. These two, that is slacks, if I work on them and if I try to increase the slacks, they will actually make me a loss of minus m per unit. If I increase 1 unit of S1, I will be in a loss of minus m. So I do not wish to be in a loss of any quantity. So these are zeros, no difference. These are negatives, meaning loss. These two are positive. Yes, students do tend to get confused that this is, sir, 4m minus 4. How are we assured that it is a positive quantity? Sir, this is 9m minus 1. How can we be assured that this is a positive quantity? And then next question that students ask is, sir, this is 9m minus 9. If it were a 9m minus 42, how can we be assured that this will be positive? We are always assured that this is positive. Why? Because what is m? Big positive number. M is a big positive number, big to the tune of any number of our formulation. May it be objective function, may it be our constraints. It is larger than any possible number in our solution. In previous lecture, I told you, assume m to be, let's say, 10,000. Now, if m is 10,000, then what does this become? 40,000 minus 4, almost 40,000. What about this? 90,000 minus 42, almost 90,000. So, who is larger? This is what we mean by big M. By big M, I mean I am ensuring that these numbers which are being added, which are being subtracted, they cannot change the value of M. M is so large that it is independent of whether 4 is being subtracted, whether 42 is being subtracted, whether 400 is being added. If 400 is being added, still 9m will be larger, because these numbers are literally irrelevant. These numbers come into play only when I am talking of 4m minus 3, 4m minus 7. Obviously, in this case, this will be larger, because this will be 40,000 minus 3. that is 39,997. This will be 40,000 minus 7, that is 39,993. So yes, here this will be larger, definitely it will be larger, but so long as there is a difference in coefficient of m, we are very clear 9m is greater than 4m, irrespective of what numbers are being added or subtracted from them. So for now, who is the largest one? 9m minus 1. So this gives me my key row, key column. X2 is my incoming variable. What about outgoing variable? B divided by A. Theta is B divided by A. B divided by A. This is our key column. B divided by A would be 20 divided by 4, 5, 15 divided by 5, 3. This is the least positive. Most positive is incoming variable, least positive is outgoing variable. A2 is going out of my solution. I had A2 in my IBFS, but now A2 is going out. A2 is going out because it is the smallest ratio in theta. This becomes my key row and this becomes my key element. Now what next? What is our next step? Our next step is our new matrix. We have x1, we have x2, we have s1, we have s2, and now another new difference. Whenever an artificial variable goes out of my solution, artificial variable was my solution. In IBFS, A1 and A2 were my solutions. But whenever artificial variable goes out of solution, it goes out of my complete solution. I forget about A2. A2 has been kicked out and A2 will be kicked out from here also. Because these are artificial variables. I want to get rid of them. I have no idea what A1 is. I have no idea what A2 is. I just needed them to start my problem. So I used them, but as soon as they go out of my solution, just for once, I remove them completely from my solution. I discard them completely from further calculations. So whenever an artificial variable becomes outgoing variable, it actually goes out of complete solution. If you remember previous questions, even if S2 would have moved out of here, we would have entertained S2 over here. Because there will be questions where S2 might go out, because for present situation S2 is not a good proposition, but later on S2 might come back into my solution. It is possible that S2 becomes outgoing from here and then enters at some other place, because it is an iterative process. For now S2 might not look attractive, later S2 might look attractive. So S2 decision variables, slack variables, surplus variables are not removed, but as soon as an artificial variable goes out, I remove it from complete calculation. Now I will never talk of A2. Now, what are the contributions of these variables? We have a 4, 1, 0, 0 and m. What are my solutions? I have A1, A2 has been replaced by x2. Their contributions are A1 is m, x2 is 1. Next big issue is how to transfer them. Now we know how do we transfer them. We have our two rules. What are those rules? One rule is applicable for key row, that is divide all variables by key element. For key row, the rule is divide all variables by key element. And second rule is old row I minus key column element I multiplied by modified key row is equal to new row. These are the two rules we will be using. So this is my key row, I will use first rule. This is any other row, I will use second rule. So first rule is divide all variables by key element. Divide 1 by 5. 1 by 5. 5 by 5 would be a 1. 0 by 5 would be a 0. Minus 1 by 5. and 0 by 5 would be a 0. A2 is gone from here. A2 is never coming in my solution. 15 by 5 would give me a 3. So I have transferred my key row. What about my other row? Old row, that is 3, 4, minus 1, 0, 1. Remember, we have 3, 4, minus 1, 0, 1. This is not being entertained from here on because it is A2. It is out. Last one would be 20. Old row minus key column element I. Key column, we are talking of first row. So, key column element 1. Key column element 1 is 4. You see how fast this process has become within a span of 2-3 questions. So, if you practice some 5-10 questions, this process will be very smooth. We need not remember any of these things, that I need to add A, that I cannot start with negative. Just in a span of 5-10 questions, we can run through these simplex questions. Anyways, we have old row, we have key column element, we need modified key row. Modified key row is over here, 1 by 5, 1, 0. This is minus 1 by 5. So, I will put a minus over here, making it plus. Then I have a 0 and 3. This will become 15 minus 4, making it 11 by 5. 0, minus 1, 4 by 5, 1, 4 3s are 12, 20 minus 12 would be in 8. So, I get 11 by 5, 0, minus 1, 4 by 5, 1 and 8. This is my new simplex table. What next? I need to find out Zj. Zj would be all columns with their contributions. 11 by 5 into m. 11 by 5 into m would be 11m by 5, and this would be a 1 by 5 plus 1 by 5. This would be a 0 plus 1 minus m plus 0. This would be 4m by 5, 4m by 5, and the next is minus 1 by 5, and last one would be in m. So, we have Cj, we have Zj. Now, I need to find out Zj minus Cj. M minus m, 0. 4m minus 1, both have 5 as a denominator. So, we can take LCM as 5. Here we have a 0. So, this will become 4m minus 1 upon 5, minus m, 0, minus m, 1 minus 1, 0. This is, both have denominators of 5. So, we can say that this will become 11m plus 1. This is 4. So, if we take LCM, we will get an LCM of 5. This will become 20. 4 5s are 20 upon 5. If you solve this further, you will get 11m plus 21 upon 5. This is 4m minus 1 upon 5. Now, if we look at all these values in net evaluation row of Zj minus Cj, remember net evaluation row is Cj minus Zj for maximization. For minimization, it becomes Zj minus Cj. So, if we look at all these values, this is 0, this is 0, this is negative. These three are out. These two are not adding or subtracting anything in my profit. This is actually subtracting something from my profit. So, these three are gone. What about these two? Now, these two are very hard to imagine. Let us see what are these. 4m minus 1 upon 5. This can be written as 4m minus 5 upon minus 1 by 5. Then next is 11m by 5 plus 21 is equal to 11m by 5 plus 21 by 5. Now, I told you that m's are so big that these numbers literally have no capacity to change the value of the m. So, what I can say is this is literally irrelevant. If this is irrelevant, can I remove it from my consideration? Okay, I'll remove it from my consideration. Now, which one of these two is larger? Both have denominators of 5. So base is same. If both denominators are same, then base is same. Then who is larger, 4m or 11m? 11m is larger, meaning this is larger. So I have my key column. And what will be my key row? Theta is equal to B by A. Now everything is very close over here. I'll use some other pen. 8 by 11 by 5. 8 by 11 by 5. 8 remains same, 5 by 11 gets flipped. So you get 40 by 11. It is 3 point something. This one would be 3 divided by 1 by 5, making it 3. This gets flipped, 5 by 1, making it 15. So this will be 3 point something, this will be 15. So obviously which is less? This is less. So I have my incoming variable, I have my outgoing variable. Incoming is x1, outgoing is a1. This is my outgoing variable and this is key element. So can we move this to our next table? Our next table would be x1, x2, s1, s2. Remember, a1 is outgoing variable. Whenever an artificial variable becomes outgoing variable, it is out forever. a1 will not come here also. So I have a b and theta. a1 and a2, both artificial variables are out of my calculation. a1 is being replaced by x1 and x2. Contributions being 4, 1, 0 and 0. Contributions being 4 and 1. Now, let me transfer my key row. The rule for key row is divide all elements by key element. 11 by 5 divided by 11 by 5 would be a 1, 0, minus 5 by 11, 4 by 5 divided by 11 by 5. 5 will cancel out, I will get a 4 by 11. And 8 divided by 11 by 5 would be 40 by 11. So this is what we get. Now, what will be the rule for this? The rule for this will be old row. Our old row is this one. 1 by 5, 1, 0, minus 1 by 5, 1 by 5, 1, 0, minus 1 by 5. This I am not considering because a1 is out. Last one would be 3. Old row minus key column element I. Key column, we are talking of second row, so element 2. It will be 1 by 5, 1 by 5, multiplied by modified key row. This is our modified key row. 1, 0, minus, let us put this minus over here, making it 5 by 11, 4 by 11, and last one is 40 by 11. This becomes 1 by 5 minus 1 by 5, 0. This becomes 1. This becomes 5, 5 cancelled out, 1 by 11. This is minus 11, minus 4, making it minus 15 by 55. And this last one would be 11, 5. 55, 55 multiplied by 3, 165, 165 minus 40, 125 by 55. 165 minus 40, 125 by 55. So this is what we get over here. What do we get? 0, 1, 1 by 11. Now you could simplify this because we are having all denominators as 11. So if we simplify this, we get, we can cancel it with 5. So it will become minus 3 by 11. So now everything is 11, it will be easy to multiply and subtract and add. Now we can even simplify this because this is 11. If we cancel it with 5, this will become 25 upon 11. 25 by 11. So this is what we get in our second row. We had Cj, we had Zj. Now let us find out values of Zj. Values of Zj would be 4. This will become 0. Then 0 plus 1 is 1. This will become minus 20 minus 1. Minus 20 plus 1, minus 19 by 11. And then this would be 16. 16 minus 3. 13 by 11. Next, if we find out Zj minus Cj, Zj minus Cj, because we are solving minimization problem. 4 minus 4 is 0, 1 minus 1 is 0, minus 19 by 11 minus 0, 13 by 11. Zeros, they'll neither improve our solution nor will they worsen our solution. They are neither increasing nor decreasing. This is actually a negative quantity, so it will worsen my solution. But this has a potential. So 13 by 11 gives me my key column. So now that we have our key column, we need to find out our key row. How do we find out key row? Theta will be B by A. As soon as we get our key column, here is my key column. This is 11. Fine. So it will be 40 by 11 divided by 4 by 11. 40 by 11 divided by 4 by 11, making it 40 by 11. 11 by 4 getting flipped. 10. This one will be something negative because this is negative. So we do not consider negatives in theta. We take the maximum positive from net evaluation row and we take minimum positive from theta. We do not take minimum value, we take minimum positive value. So this is negative, so we are rejecting it. Minimum positive would be 10. So now I have my key column, I have my key row, and so I can say that I have my incoming variable of S2 and my outgoing variable is X1. So we'll be needing one more table. Now we need to make some space for our tables and for our calculations. So what I can do is, I can try to make up some space over here and then we'll do calculations in that corner. And we'll use some other color for, completely some other color for everything. B and theta, we have X1, X2, S1, S2 with their contributions of 4, 1, 0, 0. S2 is incoming variable, X1 is outgoing. So we have S2, X2 with their contributions of 0 and X2 is giving me a contribution of 1. Now we need to transfer these rows to our new table. Divide all elements of key row by key element. Key element is 4 by 11. 1 divided by 4 by 11. 1 divided by 4 by 11. 1 divided by 4 by 11, making it 1. 11 by 4 gets flipped. So we have a 11 by 4. This becomes 0. minus 5 by 11, minus 5 by 11 and divided by 4 by 11. Let me write it directly, flipped. It was 4 by 11, but I have flipped it completely. So it is minus 5 by 4. Minus 5 by 4, and this one would be 4 by 11 by 4 by 11, 40 by 11, 40 by 11 divided by 11 by 4, 10. Now today we have not checked if our tables are correct. How do we check if our tables are correct? We can make a quick check on our tables. This was our first table. This was our second table, third table, and this would be our fourth table. Identity, A1 is 1, everything else in column is 0. A2, intersection is 1, everything else is 0. This was intact. Second table, A1 is 1, remaining column is 0. X2 is 1, remaining column is 0. So it looks like we are going on right track. Over here, X1 is 1, remaining column is 0, X2 is 1, remaining column is 0. And now we are proceeding further. So we'll see after some time. Now remaining elements, what is our formula? Our formula is old row, that is 0, 1, 1 by 11, minus 3 by 11, and then there is a 25 by 11 also. I'll write it over here, then we'll remove it. Old row minus key column element I. This is our key column, element I is minus 3 by 11. Minus 3 by 11. So I'll make it a plus 3 by 11 because minus will cancel out. So I get 3 by 11, 3 by 11, 3 by 11, and this will become 3 by 11. Multiplied by modified key row. This is my modified key row. 11 by 4, 0. Multiplied by 11 by 4, 0, minus 5 by 4. So minus 5 by 4 would again make it a minus, sorry, it was here, minus 5 by 4, then there is a 1 and 10, 1 and this one is 10. Now can we solve these? 11 will cancel out, it will become a 3 by 4, this will become a 1, 1 by 11, you'll get a 4, 4 minus 15, minus 11 by 44, making it minus 1 by 4, it will become 4, yes, minus 11 by 44, and then this will become 0. And then this is 25 plus 30, that is 55 by 11, 55 by 11 making it 5. So what do we get? We get 3 by 4, 1, 3 by 4, 1, minus 1 by 4, then there is a 0 and 5. This is my new table. Let me check it. S2, 1, column is 0. X2, 1, remaining column is 0. So it looks like our tables are correct. If this is Cj, let this be Zj. Multiply all columns with their respective contributions. First column. Now this is 0, so everything this will become 0. When we are adding, all these will contribute as 0 because they will be multiplied to 0. So we get directly 3 by 4. We get 1, here I get a minus 1 by 4 and here I get a 1. So when I go for Zj minus Cj, 1 minus 0, oh sorry, this was 1 into 0, 0 into 1 plus 1 into 0, this will be 0, minus 1, 0 minus 0, 0. Minus 1 by 4, 0, minus 1 by 4, 1 minus 1, 0, 3 by 4 minus 4, where can we calculate it? 3 by 4 minus 4, making it 16. 16 minus 3, minus 13 by 4. Either ways it is negative. So now we see that we have either zeros or negatives. So at this point we can stop and we can say that we have found out our best possible solution. We have found out our optimum solution. And what is that optimum solution? That optimum solution is that do not produce even a single unit of x1. Don't go for x1. Only concentrate on x2. My optimum solution is optimum solution. What is my optimum solution? x2 is equal to 5, making Zmin. Zmin is 4 into x1. 4 into x1. x1 is 0. We are not producing any x1. You can write down x1 as 0. Why are we putting x1 as 0? Because x1 is not here. My solution suggests that s2 should be 10, x2 should be 5. It is not talking of x1. So x1 is 0. So x1 is 0, x2 is 5. Solution becomes 4 into x1. 4 into 0 plus x2. So final solution is x2 is equal to 5, Zmin is equal to 5. This is my final solution. The board got a bit crowded, but in any case I believe everything is visible. I'm not sure if it is visible over there in video or not, but I've tried my best to keep everything within visible limits. So this is our solution. This was our very first question and we came across 3 different things in this question. First was minimization. How do we take care of minimization? Zj minus Cj. Instead of Cj minus Zj, just go with Zj minus Cj. Taken care of Zmin. How do we take care of greater than? Along with every surplus variable, add an artificial variable. Because it is greater, it has a surplus, I remove something, when I remove it becomes negative, I put an artificial variable. So this is taken care of by Zj minus Cj. Greater thans are taken care of by minus surplus plus artificial. And how is artificial taken care of? By m. In minimization it is plus m. If we come across maximization, it will become minus m. We'll take such problems also where we'll be having mixed. And then third thing that we saw was RHS was negative. If RHS is negative, how do we sort it out? We multiply it to minus 1 to change it, to convert it. When you multiplied it to minus 1, it got converted. So my second constraint was, this was not my second constraint, this was my second constraint. So my first constraint, second constraint again became greater than, so I went with this. So we learned 3 new things over here, and this is the complete solution. First, second, third and fourth table. I hope this helps in clearing some doubts about simplex, about greater than inequalities, about minimization. Minimization is simply this. Less than is simply minus S1 plus A1. So this was it for today's lecture. We'll take one more question on almost similar lines and then we'll proceed to degeneracy, two-phase method, integer programming and remaining topics. So this was it for today's lecture. If you have any queries, if there is something that I've missed, if there is some calculation that has gone wrong, it does happen on board. So you can leave it in comment section. I'll try to rectify it, I'll try to clarify it. And do subscribe to this channel if you have not already subscribed to. And thanks for watching. Bye bye. Take care.